So, good afternoon, everybody. Welcome back to lecture number 22. Can anyone sit here, please, to verify the cameras not shutting down? Better. So today, last time in the test, we had the example that you do not like. And what was the confusing part in the test is, in the test what we had, I gave you the phase equation because I looked at your cheat sheet and it has V phase, okay? So if I give you the line to line, some of you would use this equation in the cheat sheet, which is for phase. So thank you for pointing this out, okay? So anyway, there was no mistake in the test. Instead of line to line, I gave you the phase quantity. We'll accept both solutions, even though I don't think anybody will do the other solution. Okay? One common mistake when I was looking at, I haven't started grading, is how many of you regenerative braking in the MCQ, they said it's plugging? Lots of you. And I told you, go back to the YouTube video, and I told you this is a trick question. صح ولا لا? Who remember? So that's why if you watch, I told you, if you put regenerative braking in the plugging mode, it's wrong. Regenerative braking is in the generation mode. Plugging mode is something else. It's where you reverse the phase sequence.
Sudden braking, I think.
It's the sudden braking. It's a sudden braking, okay? So this is the equation that had the 3. If you don't have a 3, it would match the same. And again, see, I even left it in the slide. There's a life lesson to fill it at home. This time, I actually copied this, made the colors, and I asked you to fill. Most of you got this wrong. Very few got it right. And some of you got this wrong. Everybody got else correct, voltage. But this was an easy 1 point for the exam. Guaranteed. I don't know why you don't want to memorize. We're not physics 102 anymore. We are not physics 102 anymore. We're studying things that are used in industry, practice. So I'm not asking you to memorize those. This card, when you go and work for induction machines company, you always have to remember how to use this table. Okay? So if they ask you in the interview question, under linear load, you change the poles, as we will see today. What will be the equation? When you only change slip and poles. Slip and poles equal to 1 minus S1 over 1 minus S2, P2 over P1. Note that we're reversing the order because it goes to the original equation. So those, you can fill the white blank table using only the information in the first row and the first column. Clear? هذه 1 minus S1 F1 P2, it studies the impact on the torque ratio if you change one of the quantities. For example, if you change F1, torque 1 would probably be proportional with respect to torque 2. So we increase the torque on the load. I want to emphasize one important point. Do you remember this curve? This is what we call the capability curve for induction machine. When you have the torque, let's say a linear torque, this torque equal constant K, this point is the operating point. So the operating point is the intersection between the torque and the capability curve. This is the capability of your motor. Okay, this information is not written in the slide, I want you to understand it. If you see a curve like that, this motor may be class D. This is also a capability. and the operating point is the intersection where torque equal K with the capability. If you increase the torque to K plus delta, what do you note? We reduce the speed or increase the slip, and we operate at a different point. Clear? So that's how to define the operating point of your curve. Another thing is, what if I flip the curve to be omega with torque? How would it look like? It will look like something. So this is the starting torque. Something like that. Let me fix it. Where it will look like something like that. Okay? So what I'm doing here is I'm reversing the order of the axis. So what will happen? We're done with voltage control. We're done with adding resistance. The third technique is to do pole changing control. What if I change the number of poles? Is this doable? Yes, it is doable. How? By changing the connections. Here I have A, B, D, C in parallel. Here I have them in series. So now I increase number of poles by having the coils wrapped this way compared to this way. Okay? Now, this set of coil, they would create 12 poles in my stator, while this set of coil would create 6 poles. Of course, 6 poles is faster than 12 poles. So this is how I change the number of poles. They already have pre-configured. Yes?
Can you count them? Because I don't see the video.
No, you can't count. It doesn't mean 1, 2, 3, 4, 5, 6 poles. No,
Okay.
that's not. Poles, these are coils. Poles are where the peak points of flux meet. So if you connect them at a certain configuration and you power your machine, poles will be created. If you use this configuration, this L, these two in parallel, so if they are in parallel, your impedance will be less. You will have the coils wrapped in a way to generate 6 poles. If you extend them in series, like what we did with A, B, C, D, your L will be more. So you have more magnets, you have more storage capability. Then you have more number of poles. Now, how exactly you space the coils that you extended is a question that's beyond the scope of this course. It's usually graduate level. That's why you master's degree are not waste of time and power.
ما نقدر نقول بداية الكويل بول نهاية الكويل
No.
because it's like north and south.
No, these, how many slots in your machine? You have 36, 20, 20, sometimes you have 40 slots. You fit these coils, so maybe each coil would fit 5 slots. Get it? But this is equivalent circuit if you extend all of them. Okay? Keep in mind the stator has slots. Each slot has one coil. This is not a one coil. This coil may be shared by 5 or 6 slots where you insert it. Get it?
Yes.
The idea here is the effective L. If you double it, you should have double poles. That's the idea, that's the concept. How to wire them, we did not cover it. This is difficult. This is another graduate level course. Okay? And this course is not offered. Last time it was offered in KFUPM, it was in the 1994. The graduate level course for this. So these are the equations. What do you notice if you change number of poles? The synchronous speed would decrease. Maximum slip would it change?
No.
No. There is no P here. Because E is what? What's X equivalent? Is J omega L. Would omega change? It has to do with the supply, electrical. This is 2 pi F, this is 2 pi F, this is electrical omega, not mechanical. The X equivalent, L, when you calculate it with L, this is electrical quantity, E to 13. It's not mechanical, this is mechanical. How about maximum torque? No. How about real torque? No. Why?
How will it be affected when you are changing the synchronous speed by changing the poles?
Wait. If you change the synchronous speed, yeah, you change. If you change the synchronous speed, you change these two quantities. You're right. If you change NS, you change omega S, it changes maximum torque. If you change NS, you change omega S, it changes the torque. So you're right. That was your question?
It's also about the X equivalent.
X equivalent has nothing to do with the synchronous speed.
No, with if we are increasing the inductors with the configuration. So how will it not increase when you are having it in series instead of the parallel?
Because R2 prime will also change.
Why will it change?
Each one of those inductors have R.
Okay.
So if you cut the R over X by the same quantity,
It will not change.
yeah. So note that, can I draw a curve with the slip? So here a slip from 0 to 1. Here for this curve, the slip is from 0 to 1. So the slip is relative. So the maximum slip at the maximum torque, they're almost the same for two different poles. And each curve has a slip curve. They have different omega, but they have different slip curve. So now this is not used too much. What are the consequences? Synchronous speed decreases, starting torque decreases, maximum torque decreases. Disadvantages only valid for steps. There is not wide range. You only change the speed depending on the synchronous speed, which is usually multiple of 2. Because if you have, it is multiple by half, right? Multiple by half.
Yeah.
It's a multiple by half.
Yes.
So if you do the speed for a very large number of poles, you would increase it by 50% every time. Okay? Not multiple of half, by a certain fraction. By a certain fraction. For example, between 4 pole and 2 pole is 18 RPM. You cannot have something in the middle. That's the idea. Not suitable for starting at constant torque. Why? Because the constant torque here drops. Can you see it? The starting torque here drops as we increase number of poles. So if you have a constant torque, maybe that's constant torque, maybe this way. Maybe here you will not be able to drive your load. So any question about pole changing control? Is it used? Very rare applications, and very specific application, where you require changing number of poles. This is usually by design. So let's go to the fourth type. So what we have, added resistance, voltage, pole changing, and now we have frequency. So what will happen to the frequency? Look at the equations. We change omega S, we change X equivalent now, because we change the omega, the electrical omega, the 2 pi 60. We change the synchronous speed. So motor generator set was used to generate a supply with variable frequency. This is before power electronics, we used to have fixed 60 Hertz from the grid, 1950s, 1940s. Then we had the power electronics, where we had the ability to change the frequency of the sinusoidal signal. Now, easily you have it in the lab, the E370. You change the frequency by changing one knob, correct? So this one knob is the power electronics. So imagine having this knob to change the supply on the induction machine. So frequency changing can be obtained by 3 different methods. The last one is the most common one. The first one is AC voltage controller on and off method for only large inertia machines. So for large inertia machines, big machines, the way it works, if you have V on would equal to duty cycle 1 over time times the voltage of the supply, and V off, you would have it at a certain T minus D over T V of the supply. So if you increase D1 or the duty cycle, you keep it on more of the time. Then you turn it off. You just turn the supply on and off using thyristors, maybe, or using something that basically you're reducing the RMS value of the supply. So this is method number 1. Cycloconverter is an old device that was invented very old time using basic power electronics that's now rarely used. But the most common one is back-to-back converter, or what we call it, variable speed drive. Another name of it, variable speed inverter. It has 2 names. Variable speed drive, variable speed inverter. This is the only way to control frequency. However, do you think variable speed drives only control the frequency? No. If you get to play with the frequency of the signal, what prevents you from playing with the voltage? So this is used for V over F, because V over F is sounds more technical and better than frequency control. What are the bad things? Let's look at the curve. Don't we notice that the maximum torque decreases? So clearly this is going to be here. Let's look for it. T max reduced while we increase it. So if we increase the frequency, we increase synchronous speed, which means 1 over omega s becomes larger, so T max will be less. What else we have? Also we have starting torque reduces. It's not mentioned here. Write it down. And we have, at very low frequency, we have core saturation. Do you remember EE360? Do you remember the saturation curve with respect to frequency? Do you remember this curve?
I think.
You remember. So look at it. Anyway, it turns out we will have core saturation where, if we have lower frequency. So if you're driving your motor with very low speeds, you may end up with the saturation. You're not magnetizing your core enough. Okay? I can show it to you. Well, later. I'll try to maybe. I need to, but it's in the module number 2, the magnetic circuits in E365 that I shared. What is the biggest advantage is you can drive whatever speed you want. You have very wide range from 0 all the way to 3600. So this, to me, this looks like a 4-pole machine that you reduce its frequency, and then here at the lower speeds we do not have the curves because we have saturation. Okay? Again, since we already have complicated back-to-back converters or variable speed drive or variable speed inverters, why not we use them in the region of constant flux? So it turned out that if you increase the frequency alone of the machine, your torque max drops. And here you operate at what we call flux weakening. This region is flux weakening. That's the reason why you have lower torque. Is there is magnetization, but the flux is getting dropped because the voltage cannot maintain such high frequency. Clear? The voltage cannot maintain or cannot drive such high frequency circuit. So if you look at one of the equations, if you go back to the flux equations, you will find that they are a function of, so usually the flux is a function of V over F. You will find V on the top, frequency at the bottom. That's why, if you look at torque equation, it's V over F. It's a V square over F. So if you control V over F, you can maintain the maximum torque. And where torque comes from? Comes from flux linked current. So the flux linked current is proportional to the torque, which is proportional to V over omega, which is V over F ratio. So why not we use the variable voltage, variable frequency control, which is the constant flux control. This is the variable frequency drive or variable speed drive or variable speed inverter. Different names. Variable speed drive, variable speed inverter. Now variable speed inverter, if the last stage is an inverter, it's called variable speed inverter. Variable speed drive is general. If you have another technology, it's more generic name. Then variable frequency drive or variable voltage, variable frequency, all these names are commonly used in industry. They all mean the same thing. Change the supply voltage and the supply frequency. Or we call it V over F control. So it is excellent for both starting and speed control because what? Maximum torque is constant. Note that the maximum torque here is constant. The starting torque increases if you increase. The starting torque increases if you have V over F. So 1 over F, if 1 over F increases, basically if F1 larger than F2 larger than F3, if you have 1 over F, it will increase. So basically if you have F3 less than F2, you can increase, you can control it. Starting torque is constant because the flux is constant. Remember, current is related with flux and it has wide range of speed control. You have different speeds. So this is the current. If you only change the frequency, you will have F1, F2 and F3. The starting current would change a little bit. However, if you maintain V over F, it will bring the gap closer because the flux is constant. What are the limits? One important thing I want you to learn with the V over F, and this is very important. The voltage varying in variable voltage, variable frequency control is limited by rated value. Does it make sense? It means if your machine is rated at 440 phase or 440 line to line, in V over F control, you change the voltage until you reach that level. Do not exceed rated. Why? Because if you exceed rated voltage, you will enter what we call the weakening region. Beyond the rated voltage, only frequency can be increased to control the motor, and that's what we call the flux weakening or overspeed. So if we increase here beyond 1, we only change the frequency. Controlling the frequency over the rated value, 60 Hz for instance, means changing both synchronous speed and motor speed. And all of the time motoring mode, the motor speed is less than the synchronous speed. So here, yes, we increase the speed, but we're maintaining the voltage. So that's the proper way of doing V over F control. You increase V over F until you reach FV rated, then you put a limit on the V rated, then you only change what? The speed. Why? It has many reasons. The main reason is we enter the constant power weakening region. If you enter that region and you change the voltage, you make the problem worse. So this is one thing is by design. This is by design how to control it. So what is the limit for variable voltage, variable frequency control? Is you're capped by rated voltage. Do not exceed rated voltage. What is the other thing? Why we do not increase the rated voltage? If you increase the voltage, you have a fixed impedance, you increase the current. If you increase the current, what will happen?
Fault. Losses.
No, not fault. You will have heat
Losses.
and you have demagnetization. So you're contributing to the flux weakening. Okay? That's one of the reasons. Do not do it. After the rated voltage, only change the frequency to increase the speed. And this is the control algorithm, not required. I even don't know how the details of every block, but if you look at it, you have a reference speed, you have a measured speed from the current that you measure here in the DC side, then you have electrical error, then you have integral, so this is P, this is derivative, this is integral. This is PI controller. PI controller, the P controller gets you the voltage reference, measured again from a current limiter. So the current limiter would give you a voltage. Compared to that voltage, the command will go to the PWM. PWM give you voltage and alpha. Alpha has to do with the frequency. If you remember, alpha is the switching frequency of your drive. So alpha and V, they will be fed into your PWM back to the power electronic circuits that gives you AC. And here you get a supply from the DC link. It doesn't mean you power your motor from DC link. It means you put a DC link, and here on top you have a rectifier, and here you have your AC supply, three-phase. So you have three-phase supply, rectifier, DC link, inverter, back to your motor. Now in the DC link, you use it for control. It's not required, but as you can see, you get the current reference, you get the speed measured with the speed reference, you get an error signal. This error amplifies PI controller. The P controller will give you the voltage command. The integral controller will give you the firing angle, alpha. You use both of them to the pulse width modulator, class activity, and then you use the power electronics. You're not required to memorize this, okay? This is not required, just understand it, okay? But this is required. Here we have constant torque, constant field. After rated voltage, what will happen? We'll enter the flux weakening.
دكتور يعني عادي ننزل الفولتج تكون اندر فولتج تأثر الموتور ما تأثر.
No, do not. Just keep it fixed rated. Here you at V over F, you start with a set point of voltage, maybe 60% of rated or 80% of rated. And then you start with a very low frequency. You keep increasing them the same until you enter the flux weakening region. Then you, by that time, by design, you should have reached to V rated. And do not increase V rated, only increase the frequency to keep controlling the machine. What's the drawback here is you get drop in the maximum power because you already enter what we call the flux weakening region. V over F would make the first few curve having the same constant power. So V over F would push this curve up, would push this curve up. Maybe these two curves would stay in the weakening region. Okay? Keep in mind what are the axes here. Here the axis is electrical over base. And the other axis is omega over omega. That's the speed with respect to the base. The synchronous speed. So here at the synchronous speed, you enter the flux weakening region. Okay? Clear? I know it's hard. Is it hard?
Not really.
So try to understand. This is hard. But this one is just conceptual. So if they ask you in the interview, what is V over F? You keep it until V rated, and then you keep increasing the frequency. Why? To maintain the maximum torque. To maintain the maximum torque. Also note that the starting torque is not that different. The starting torque is not that different. This is the circuit I told you. Here we have the power electronics. Here we have the DC link. Here we have the control. We connect it to the DC link, and here we have the rectifier. This is what we call the power electronic converter. I already explained it here. This is the power electronic converter. AC source, rectifier, DC link, power electronics, and then AC. Okay, any question? I don't want to rush the example, so let's do the example in the next lecture. But for now, let's recall what we covered today. We covered, okay, this is the activity. If you haven't done it, please do it. I think only 2 have done it. Who did it?
وش نرسلك شيء يعني ولا تبي نرسلك شيء؟
Yes, I told you to send me a Word document or a PowerPoint.
نتكلم عن الوصف.
Yes. I wanted to read more about it. Okay. And what's the other activity, the bonus?
CV.
CV. If you, it's not a bonus. It's not mandatory. It's a help. Maybe it will be counted later. So we talked about change resistance, change voltage, then pole changing. What's the catch about pole changing? Is that it's not used, and it impacts synchronous speed and max and T negatively. Frequency control, what is the point? Is it impacts directly the maximum torque, etc. However, if I keep V over F constant, I can mitigate some of those disadvantages, like the maximum torque reduced with F increase. It can be kept constant until V rated. If I exceed V rated, then I have to suffer. Same for starting torque. Starting torque decreases as we increase the speed, and we have at very low frequency we have an issue of the saturation. So this curve may suffer from core saturation. And the advantage is you have a wide range. To get both of them, you keep Tmax constant, you increase the starting torque, you increase the starting current, wide range of speed control. Now, is it always a good idea to increase the... No. Is it... Why we keep starting current constant? Why this is a good thing? Because if I have a very high starting current, your motor would consume so much current, inrush current at the beginning, so that the loads around it will not have enough current to power themselves. So that's why to have it constant and known is better. So that before you make a connection of this of your machine, you know how much current it consumes, and then it will not cause a break in your breaker. And what is the limitation? It's limited by rated voltage, and this is the controller that we use. It's a PI controller to the PWM, and it uses information from the DC link. From the DC link. Okay? And this is in practice. This one is made, I think, by it's like a Siemens motor control. So these are very, very common, very programmed. At some point in industry, if you work with a company, you will see them. Okay? You will see them. Aramco, Sabic. Now, what's the new name for Saudi Electricity Company? Saudi Energy. So Saudi Energy, they have lots of them. Lots of them. Okay? Any question?
Are those the Sibacone S8?
What?
Sibacone from Siemens.
Ali?
Yes.
Yeah, I think they are from Siemens. It looks like from the buttons.
Yes, yes, yes. Sometimes.
I don't know. I think they're from Siemens.
Yes, yes, they are.
You have Siemens, you have ABB. ABB, they're very good at motors. They have, what else?
Schneider.
Schneider Electric.
Yeah, Schneider.
GE, do they control motors? Yeah. GE is known for generators.
Yes.
More for generators. And I told you about their Dammam fixing facility. Okay, let me turn it off. Any other question?